today and tomorrow I'll be talking about the baryons, the 4% universe. And in particular, I'll be talking about hydro-cosmology simulations of the baryons in the universe. Now, last week I didn't really know what I was going to talk about. Do I say more about Gordon? Do I talk about algorithms? I ended up deciding to give a couple of science talks. And first of all, I think people like science talks. And second of all, these two subjects that I'll be describing generate large amounts of data. So there are data analysis challenges that are similar in some respects to what we heard about last week, but different in some other respects. So here's my lecture plan. Today I'm going to talk about hydro-cosmology simulations of baryons in the cosmic web. In particular, talk about something called the Lyman alpha forest, and then also talk about baryon acoustic oscillation in the Lyman alpha forest. And tomorrow I'll talk about radiation hydrodynamical simulations of what I call the cosmic renaissance. This is the epoch of reionization in the first galaxies. The motivation for doing this is listed here. First of all, baryons are the part of the universe that we can see. It involves real astrophysics that is complicated and interesting. It's what I like to do is astrophysics. We can place constraints on the dark universe through our observations of the visible universe. And I would argue one can make computational discoveries. And here's a figure from a paper I wrote 15 years ago where I was describing what are the contributions from numerical models as they mature. And in the beginning, and this axis is model maturity, going from low to high. In the beginning, you derive physical insight. And that, of course, is the real reason for doing simulations. Darren emphasized that, and I agree with that. But as these models mature, you start making observational contact, and then the game is to post-dict what has been observed. And if you can do that, you feel like you're on the right track to getting the right physics in your model. But the real payoff is when you can make predictions and, in some cases, discoveries. Now, discoveries are fighting words. Observers think that they're the only people who can make a true discovery because it's empirical, it's real. But I would disagree. I think one can make a discovery by solving a set of equations that if you had the right equations and you got a good solution and you found a phenomenon for the first time, you've made a discovery. So here's just a few computational discoveries that I've been involved in or close next to. The physical nature of the Lyman alpha forest absorption systems was discovered in computers. The existence of the warm-hot intergalactic medium and the mass scale of population 3 stars. I've been involved in 2 of these 3, and I was very close by the action on the 3rd. And I'll be spending this lecture talking about this in more detail. What is hydro-cosmology? Well, I do not intend to go into this in any detail today, but basically you take your standard n-body dark matter simulation and you combine that with a hydrodynamics solver of some type, add in microphysics as appropriate, and what comes out is a cosmological simulation that includes the baryons and some of their microphysical processes. Now, this is not a new endeavor. It's been around almost as long as n-body simulations. So here's a paper from 1990 by Renyu Chen and Jerry Ostreicher. They collaborated with Tony Jameson, who was in the air department. He developed numerical methods for calculating airflow over wings and aircraft. Their paper, Universe in a Box, it describes what we all do. We put a piece of the universe in a periodic cube, and here you can see plots of baryon density, dark matter density, and baryon temperature. You know, fairly small box by standards, but, you know, it had the essential physics in there. The adiabatic non-radiative gas dynamics was assumed, but that was good enough to get started. Here's a seminal paper by Gus Everard, where he used smooth particle hydrodynamics coupled to n-body techniques to simulate the formation of galaxy clusters, again, assuming non-radiative gas dynamics. I was switching fields from extragalactic radio jets to numerical cosmology at that time. And here's my first paper with a couple of collaborators where we looked at the fragmentation of Zeldovich pancakes in dark matter universe. And this paper was one of the first to use color raster and was also the first in hydrodynamic cosmology to include radiative cooling, which of course is what allows this pancake to fragment into pieces. Well, we've made a lot of progress since then. Computers keep getting bigger and more powerful, and I like to use big and powerful computers. And so here is not the Bolshoi simulation. It looks just like those images, but it's one of my simulations. And what you're looking at here is the distribution of baryons in a large volume. And at this scale, they look rather the same. However, if you look in detail, you'll notice that the filaments are more continuous than the dark matter counterparts. And that's, of course, because of gas pressure. Puffs things up and smooths things out. Now, I don't want to go into numerical methods. I'll just point you to a couple of websites. Everything I'm talking about has been done with the ENSO code, which is a code that was originally developed in my laboratory starting about 18 years ago. But it is now truly a community code, and you can go to this website and download the code and find out how to run the code, and lots of documentation there. But I would also like to point out that exactly 2 years ago, the first HiPACC Summer Institute was exclusively devoted to numerical hydrodynamic and m-body simulations. And here is the URL for that website, which is on the HiPACC website. And there were 5 or 6 codes presented in great detail, including the ENSO code and the ARC code, Ramsey's gadget, and some other codes. And so, I mean, for example, I gave 5 lectures on the ENSO code, and then there were hands-on sessions in the afternoon, which is all captured here. So if you really want to learn how to use these codes, I would go to this website as your entry point. Okay, so that's the introduction. Now I'd like to start lecture 1, which is on hydro-cosmology simulations of the intergalactic medium, baryons in the cosmic web. And I want to focus on a observed phenomenon called the Lyman alpha forest, which is in many respects the baryonic counterpart to galaxy large-scale structure. And although the objects themselves are absorption features in a spectrum of a quasar, the data sets are enormous, and they're statistically rich, and they contain lots of information about not just the physical state of the intergalactic medium, but the dark matter that underlies it, the power spectrum, and so forth. So this is kind of an arcane subject, and maybe you've never heard of it before. And so what I want to do today is just give you a taste for what it's all about. So the first question is, you know, coming back to the pi, 4% baryons, where are those baryons in the universe? And you may remember Joel mentioning that only 0.5% of, the full pie is in the form of galaxies. So that means 3.5% is somewhere else. And that somewhere else is in the intergalactic medium. So here is a result from a paper by Renyu Chen and Jerry Ostreicher, published in the late 90s, where they did a hydrodynamic cosmological simulation. And they just evolved the universe from down to redshift 0. Where are the baryons and what state are they in? And here you see the volume fraction versus redshift. This is the mass fraction. And then here you've got the intergalactic medium binned according to its temperature, and then you've got galaxies. And you'll notice on the volume fraction, you don't even see the galaxies. What that means is if you just look out into space in a random direction, by and large, you're not going to see a galaxy. You're going to see the intergalactic medium, if you have some way of detecting it. Over here, the mass fraction, you can see the galaxies rising up to about 10%. This is of the baryons, so 10% of the 4% in galaxies. And the rest is in the intergalactic medium in various phases. The photoionized phase, the shock-heated phase, and the highly shock-heated phase. So how do we observe the intergalactic medium? Well, we have these wonderful things called quasars, which are very bright and very distant. And when we look at a quasar and we take a spectrum, we are getting a line-of-sight sampling of the universe over path lengths that are gigaparsecs long. Truly enormous path lengths. And here is a real spectrum. So here's the background quasar, which is just a light bulb. And it is illuminating the universe with ultraviolet light. And what you see is a spectrum that looks like this. Fairly featureless spectrum on the red side of the intrinsic emission coming from the quasar AGN itself. And then on the blue side, you see what on this scale looks like noise, but in fact, it's all data. And you see here, for example, if this line of sight goes through the outskirts of a galaxy, the neutral hydrogen will take a big absorption cut out of that, and maybe another galaxy here, substantial absorption. But all of this absorption that you see here is the Lyman alpha forest. And if you observe that with a very high resolution spectrograph, you get high signal to noise data like this. And you see that those spikes actually resolve into beautiful Gaussian or Voigt profile absorption features, most of which are hydrogen Lyman alpha. In fact, in this section here, probably all of these are hydrogen Lyman alpha, 2-to-1 transition, and they're all at a different redshift along the line of sight. And so what you have here is a core sample through the universe where you're picking out absorbers at different distances and hence redshifts from the Earth. So the discovery that was made with hydrodynamic simulations in the mid-90s was what is causing that absorption. This was a discovery that was just waiting to happen, and it happened among 3 groups researching this all at the same time. And I was a part of this group here, the Zhang et al. Group. And the explanation is quite simple. If the universe has this cosmic web structure in the dark matter, then the baryons will also follow that cosmic web pattern. And if we have a distant quasar and its line of sight is passing through this filamentary stuff, and if there is neutral hydrogen in each one of these filaments, then the light will be absorbed accordingly with a redshift that corresponds to the line of sight distance. So here's, this was a state-of-the-art simulation in 1995, 128 cubed. But it was good enough to establish that this was a good representation of what was being seen. So the intergalactic medium exhibits this cosmic web structure, and the model explains the observed hydrogen absorption spectra. This is a simulated spectrum where you can see absorption features that look qualitatively very similar to the data. Now, everyone got, well, first of all, there were 3 groups that discovered this more or less simultaneously. And the interesting thing is all 3 of those groups were part of a single NSF-funded Grand Challenge team. So it was a case of what you call co-opetition. And in fact, you know, many of these students went on to become postdocs, swapping institutions, collaborating with one another. It was a wonderful thing. But because we had 3 independent groups claiming this at the same time, and it explained the data so well that there was just this revolution in thought almost overnight that, yes, this was the explanation. But everyone got very excited because the Lyman alpha absorption directly probes the dark matter distribution. So what I'm showing here, the heavy line is the local gas, the log of the gas over density, and it's going up and down. And then the dashed line is the dark matter over density, and it's going up and down in exactly more or less the same way as the baryons. And then up here is the simulated spectrum, where you can see that there's a correspondence between overdensities and absorption. However, you've got various things entering here. You've got the peculiar velocity of the gas, you know, shifting the line away from exactly where the peak is in the density and so forth. You've got thermal broadening. You've got, in other words, this spectrum is a kind of a convolution of this density structure. But nonetheless, everyone got excited because if one knew how this really worked in detail, you could go from the observations of the spectra to the underlying dark matter along tremendously long lines of sight to tremendously large samples of quasars. So you had a new kind of large-scale structure that you could explore. So now I'd like to talk about, you know, what happened next and talk about cosmology from the Lyman alpha forest. Talk a little bit about what is measured, the standard model for the Lyman alpha forest. Talk about the early flush of success with the good agreement between simulations and observations. Talk about how the dark matter power spectrum is estimated, and then come back to where we are today. And in a nutshell, nobody doubts that this is the paradigm, the correct paradigm. But as observations improve and as simulations improve, you go from 10% comparisons to 1% comparisons. And inevitably, some things start disagreeing. And it's that disagreement that really drives the research and makes science interesting. Basically, you should not be unhappy when things disagree. You should rejoice because it's an opportunity to ask some new questions and learn some new things. Okay, so the standard model can be described very simply, that you take your favorite cosmological model, and I should point out that when this revolution occurred was before the lambda CDM got locked into everybody's mind. I mean, remember, that was 97, 98, 99. This stuff happened 94, 96. We were still in that phase of cosmological research where we were playing with different cosmological models. So you take your favorite model. We have an intergalactic medium of pure hydrogen and helium gas that was produced by the Big Bang. And here's the important part. This gas is photoionized by a homogeneous but evolving ultraviolet background due to galaxies and quasars. And we have very good observations of the galaxy and quasar luminosity functions. And we are able to calculate, from physics, what that ultraviolet background looks like. And it's high, it's strong, it's sufficient to ionize the intergalactic medium to almost 1 part in 10 to the 5. So, basically one particle out of 10 to the 5 is a neutral hydrogen atom in the typical intergalactic medium. So when we see this H1 absorption, we're actually looking at a tracer of the baryons, which in turn are tracers of the dark matter. Nonetheless, we have good estimates of what this is the mean intensity of the ultraviolet background as a function of redshift. And that photoionizes this gas. And then the Lyman alpha forest is due to optically thin absorption in highly ionized gas in intergalactic filaments tracing the dark matter distribution. A byproduct of this standard model is that things called Lyman limit systems and damp Lyman alpha systems, which are the higher column density absorbers that you saw in that spectrum, the deep absorption troughs, those fall out of this model as well as just higher column density things. These are optically thick absorption in denser ionized gas bound to halos, galaxies. So that's the model in a nutshell. So what is observed? So back to this slide from this paper by Kirkman and Tytler, and they were here. I mean, Tytler is still here, but Kirkman has gone on to private industry. They made very high-resolution Keck observations, and there you see this spectrum again. And these numbers up here, there's 2 numbers for every line. There is a H1 column density, the log thereof, so 13.6 means that 10 to the 13.6 H1 atoms in that absorber. And then this 21 is the Doppler width. This is in kilometers a second. And so you see lots of numbers here. And in their data paper, you have page after page after page of tables from one quasar, just one quasar. And you see some metal lines here, but most of the lines are H1. And here you've got the column density, you've got the Doppler width, you've got errors, and you've got the observed wavelength. So one quasar gives you hundreds and hundreds of these absorbers, and by now we have thousands of quasars. So we've got an enormous data set. Okay, so you want to compare with that. So you do a simulation, and basically the flux is e to the minus tau, and tau is calculated by just shooting a ray through the box and looking at the local hydrogen density, multiplying by the absorption cross-section CDT. And this can be converted into redshift, and a redshift integration like this, which is from this paper by my student. And this is fundamentally some kind of convolution. You just shoot a ray, and you're basically doing a convolution over various things that you've simulated. The peculiar velocity of the gas in that cell. This B is the Doppler broadening, which depends on the temperature in that cell. Here is the neutral hydrogen density, which you've calculated from ionization balance in that cell. And so you can construct these simulated spectra, and you then fit them using standard techniques. And so here you see the same spectrum fit in 2 ways, and you can see the Doppler widths up there. Okay, so this is what got everybody so excited. This is from my 95 paper. So the one thing you can do is you can just plot the distribution of column densities versus, so this is the number of absorbers versus their column density. And the data was already known even prior to Kirkman and Tytler. So those are the crosses there. It's the data, Pedagine 93. And the open circles are what our simulation predicted with no fudging. Boom. This is a prediction for the helium Lyman alpha forest, which still has not been observed at that level of prediction. This is the cumulative number of lines versus column density. Again, the data is the points, and the line is the simulation. Boom. Here is the observed distribution of line widths. It looks like a skewed Gaussian with a peak here at 23 kilometers per second, median line width. And here's what came out of the simulation. It looked just the same, but in fact, the line width was too high, 30 versus 23. But still, this was encouraging enough to convince most people that we were on the right track. So let me now talk about this line width a little bit. Well, before I do that, what is a Lyman alpha forest absorber? Physically, what is it? So here are some projections through our box at 4 redshifts. And the gray scale is the column density in neutral hydrogen. And the typical Lyman alpha forest range is from 12 to 14.5. And so the first thing you see is, a line of a given column density changes. I mean, its physical character changes as you go down in redshift. And that's because the universe is expanding. Recombination rates are changing. The UV background flux is changing. Everything is adjusting. But still, the typical Lyman alpha forest line at these redshifts, which is where most of the data exists, are these sorts of things. These low overdensity fluctuations in mini voids, and to a certain extent filaments, but not too overdense filaments. With the simulation, you can go in and ask lots of physical questions. Of course, we ran thousands of lines of sight through our box. And for each line of sight, we had dozens of absorption features. So we had a very large data set. And so you could correlate gas overdensity with column density, dark matter overdensity, velocity divergence. This is the peculiar velocities on top of the Hubble flow. Do these kinds of correlations. And after you've done all that and looked at it, you can ask the question, what are these? So these are sheets or filaments of low overdensity relative to the local mean density. So you can have a little fluctuation in a void that is actually below the cosmic average density, but it shows up as an absorption feature. That was a discovery. Actually, the other two groups didn't get that. We got that little nugget. They're not gravitationally bound. If you come back, this is the velocity divergence of the peculiar velocity. And you can see there's 0. And you can see a whole lot of absorption features that have a positive velocity divergence. Well, what's that all about? Well, if you've got a sheet or you've got a filament, a sheet is collapsing in one direction and it's expanding with the Hubble flow in 2 dimensions. Or a filament is collapsing in 2 dimensions and it's expanding in 1 dimension. And if you just send an arbitrary line of sight through these things, you'll pick up that expansion. So they're not gravitationally bound in 3 dimensions. We find that they're unbiased with respect to the dark matter on average, although there's quite a bit of scatter. And the gas is photoionized to about 10 to the 4 Kelvin. The size of these, the thickness of these absorbers is about the Jeans length in the intergalactic medium for those densities and temperatures. And that's about 100 kiloparsecs, which tells you that there is a scale that needs to be resolved. And our first simulations did not resolve that scale. And that turned out to be the reason for the discrepancy between that and that. But we didn't know that at the time. That's why we call it research. So a few years later, we did a resolution study, tried to converge on the properties of the Lyman alpha forest. This was with another one of my former students, Greg Bryan, who's gone off to do great things in galaxy formation. So the observed line widths reflect thermal broadening, Hubble broadening, which is both redshift, line of sight, and H1 dependent, and possibly turbulent broadening. Now, the Hubble broadening, let me explain this to you. So if we've got this pancake, and it's so thick, and it is expanding with the Hubble flow in 2 dimensions, if you shoot a random line of sight through there, 100 kiloparsecs, divided by cos theta is the path length. And that path length has significant Hubble broadening across it. So you've got to add that velocity width in to the line. It's not just thermal broadening. Hubble broadening actually dominates. So the simulated line widths are all of these things plus numerical resolution broadening. If you take this feature that's supposed to be this thick, and because your finite grid smears it out to this thick, then you're going to get Hubble broadening across this additional Hubble broadening just because of a resolution effect. And this is what we found in this paper. So what's plotted here is the median of line width, B, versus redshift for 3 different grid sizes: coarse, finer, finest. And what you see, so at a given redshift, you can see that we're not converged. We go from here to here to here. At this redshift, here to here to here. We're starting to converge, but we haven't actually converged. And the original simulations we did had a resolution up here, which is why we had a median B of 35 way up here. Nonetheless, if you do this convergence study, you can actually derive the scaling law and extrapolate to 0 cell size, which we did later. So anyway, this is showing you that this has a resolution requirement, and it's fairly severe, but not as bad as galaxies, which are really tiny. But now we have a problem. Yes?
Question on the turbulent project. Do you get like a subgrid model, or how do you go about setting that?
Nobody includes a subgrid model. And the reason is nobody is operating at those resolutions where, that would become the dominant term. You could add a subgrid model. Now, I can tell you that we've done simulations that drive the numerical broadening down so that it's subdominant, and we don't see any turbulence in these filaments. But, who knows? As the data gets more and more and more precise, it may be that that becomes necessary, but we're not there yet. So this compares the line width distribution function from the highest resolution simulation with the data. And now, at 2 redshifts, the data is the solid histogram. And now the line widths are too narrow. So, our perfect agreement has been besmirched a little bit. So, possible reasons are the cosmological model is wrong, the UV background model is wrong, the box is too small, that is to say, there's large-scale power missing in the structure formation, driving the filaments. Missing heat sources, helium-2 reionization can add heat at lower redshifts, X-rays. Missing turbulent broadening, maybe the turbulence is driven by galactic winds, and what we're really seeing is gas near galaxies. Maybe magnetic support. Lots of reasons. So I can tell you that 13 years later, this discrepancy has not been completely resolved. And so this is an opportunity for contributions by people like you, and maybe a fundamental contribution. So, of course, we weren't idle. We started looking at these things ourselves. And so this is a simulation that we did here around the turn of the century on one of our supercomputers. This is, again, you're looking at baryons. This was the first 1,000-cubed hydrodynamic cosmology simulation in the world in an 80 megaparsec box, and you're looking at the baryons here. Tridi Jenna was a student of mine, and we started looking at some of these questions. So we did 40 fully hydrodynamic simulations, varying lots of things, some of the things on that previous slide. Cosmology parameters, box size, numerical resolution, UV background intensity, and extra heating put in by hand. We did a statistical analysis and uncertainty quantification. And by taking the state-of-the-art observations, we constructed a concordance model of the universe at redshift 2. It's done in collaboration with David Teitler and David Kirkman, and so we had the best Keck data available at the time. I should point out that all of this data is available online. Jeffrey So, in fact, when he was a brand new colleague, I think you were a senior at the time, weren't you? Yeah. So we have a data collection online. It's just a web page, website. No big deal. Yeah. But if any of you should be interested in this data, it is available. So the analysis we did, we wanted to derive simple parametric fits to the relationship between inputs and outputs. Standard thing you do. So the key inputs, cosmologically speaking, is the amplitude of the matter fluctuation, two numbers that describe the UV background, gamma 912 and X228, which are normalized H1 photoionization rates and helium-2 photoheating rates. The box size, the cell resolution size. The key outputs are the mean flux, that is the mean amount of absorption through the box. Just take lots of lines of sight, calculate the absorption, just average it all out. How much light is being removed? That can be related to the effective optical depth this way. You've got your median line width, and you've got flux power at 3 wavelengths, wave numbers. So let me just tell you a little bit about the flux power. You've all heard of the matter power spectrum. The flux power is the thing we use in this field. So you've got your transmitted flux as a function of velocity along the line of sight. You turn that into an overflux by just subtracting the mean flux and dividing by the mean flux. Then you've got this overflux, flux overdensity, if you will. And then you just Fourier transform that and square it, and you've got a flux power. And so here's what they look like. Here I'm actually giving away one of the punchlines, which is that the simulations systematically underpredict the amount of flux power on large scales. So this 10 to the minus 2 corresponds to about 100 megaparsec co-moving. So these are large scales. However, it's not clear whether the observations are to fault or the simulations. There are lots of systematics that come in making the observational measurements. Anyway, these three P's are just measures of the flux power at these three wave numbers. That's all they are. And you can even see right here that the simulations do a really good job of recovering the flux power at these two scales, but are discrepant at the largest scales. So here's the table of simulations, different box sizes, different resolutions, different sigma 8s, different heating coefficients, lots of simulations. And the goal was to find the scaling relations that would relate the inputs to the outputs. And one way of seeing that we found those scaling relations is this diagram here. This is just taking every simulation and just plopping down the median line width and the effective optical depth, just raw. And then these are the scaling relations that were derived. And if you got a perfect fit, all of these points would collapse to a single point in this diagram. Now, they didn't quite do that, but they almost did that, which is telling you that the cross terms are very small. They're higher order. And the spread of these points is telling you to what accuracy you can actually scale out the effects of the different inputs. So what were our findings? Well, first of all, that after scaling out the box size and resolution effects, we could fit a wide range of sigma 8s to the observations. And the key observations were the mean flux, the line width, and the flux power at the smallest scales. We could just adjust these UV background parameters up and down and make these things fit. Using these three numbers, we could not uniquely determine these three numbers. You might think if I had three independent measurements, I could derive three independent quantities. But we could not, because it turns out that this line width and this flux power at small scales are highly correlated. They're basically measuring the same thing. Because if you think about it, if you've got a line profile like this and you Fourier transform that, that translates into a power on that scale, right? So in fact, we only had two independent measures, and that left a degeneracy between two of our outputs, and that's shown here. So we can get a wide range of sigma 8s working for us if we just modify this extra heating, this mysterious extra heating factor. Now, you could potentially remove the degeneracy using the large-scale power. That would give you a third number. But this was not explored in that paper. The box sizes were too small. And furthermore, the observational uncertainties at low K are pretty profound. But based on the scalings, we concluded that we need at least 100 megaparsec boxes with at least 50 kiloparsec resolution, which means 2,000 cube simulations. But we would prefer to have 25 kiloparsec resolution, because that's what this tells you right here. And when you go there, you're up to 4,000 cube simulations. So these are comparable to the largest M-body simulations, but without the need to resolve the halo substructure. You're resolving this smooth, fluctuating intergalactic medium. And what it tells you is Eulerian simulations on uniform grids are adequate. Well, just so happens we have a 4,000 cube simulation. Here is one. But it was not done for that purpose. This was done for the baryon acoustic oscillation, which I'll be getting to in a few minutes. But so this just shows that it's possible to do simulations of this size. But the data analysis becomes pretty heavy. I mean, a single snapshot of a simulation like this is probably about 15 terabytes. A single snapshot. And then, of course, you've got to run your lines of sight through this, construct spectra. It's a lot of analysis. And we have actually not done that. We went chasing another piece of science for a while. But that is clearly what is needed in this field going forward. So let's see. I'm going to race through a couple of slides here. They're going to be in the slide deck on the website. You can come back and look at them if you're interested. But I did want to say that this measurement of the CDM power on these scales, these purple points that Joel showed last week, these come from the Lyman alpha forest. And of course, this says, the data agrees beautifully with the observations. But in fact, this is really hard work, and only 2 papers have been published on this since the late 90s. Which tells you how difficult it is. And it's not so much the simulation side, it's the data, the observational data analysis is fraught with systematics, which you don't really appreciate until you start comparing with simulations. And that iteration between simulations and observations is still pretty raw, still pretty undeveloped. So I would say that this field is like large-scale structure was 10 years ago. And more people need to be doing it, and only in that way. I mean, look at the size of the error bars. I mean, this is really not very impressive. Furthermore, I would argue that there's a normalization that's unknown in this part of the spectrum by a factor of a few. So this is actually not so impressive once you dig into what's going on there. But let me just tell you how it's done. It's from a paper by McDonald, 2005. And that data, by the way, is the Sloan quasar. Sloan quasars. So the key ansatz is the usual one in cosmology, that the flux power, the power of the thing you're measuring is related to the underlying matter power by some kind of bias factor. That's the key ansatz in most of this work. And the idea was to evaluate this bias factor by comparing with hydro simulations. The difficulty is that the SDSS spectra is that the lines are not resolved. It's a low-resolution spectrograph. And without resolving the lines, you don't know whether it's an H1 line, a metal line. You may have galactic absorption mixed in. It's very hard to get that out. Setting the continuum level is challenging. You've got noise. Maybe the UV background is fluctuating on the scales that Sloan is observing. So in practice, B of K is estimated on large scales from non-hydrodynamic simulations, from in-body simulations that have been fixed up with prescriptions for how the baryons absorb. And so it's not really a first principles determination. So the upshot is that there's lots of systematic uncertainties, and doing the large simulations is kind of essential in order to understand what those systematics are and then deal with them. And that really hasn't happened yet. Okay, I'm going to skip over this part in order to do the last part of this talk. I do want to just say one thing. So this is kind of the punchline for the current status. This is showing the results of numerical simulations from a series of boxes that get bigger and bigger and bigger. So those are the lines, solid lines. And then the points are data. The red is high-res data, and the yellow is Sloan data, Sloan SDSS quasar data. And what you see is that the simulations, well, first of all, the flux, so this is the flux power. And the flux power actually converges quite well as we go to larger and larger boxes. And it agrees well with the observations at high wave number, small scales, but it deviates on large scales by 50 to 100%. And at this point, we don't know whether the observations are overestimating the power or the simulations are underestimating the power. That's a great question, isn't it? That'd be a good PhD thesis. Jeffrey, why didn't I suggest that to you? I don't know. My mind was going somewhere else, to reionization. But anyway, this is hanging out there for some bright student to deal with. So in the last few minutes of my talk, I want to talk about BAO. It's been mentioned a few times. This is really where a lot of excitement is happening in observational cosmology, not only on the galaxy large-scale structure side, but also on the Lyman alpha forest side. So, BAO in the Lyman alpha forest. This is a project that I started about 5 years ago. And the whole idea is we want to measure the expansion history of the universe to high precision. And one standard way is using standard candles. But if we had a standard ruler, that would be good too. And that standard ruler is the baryon acoustic oscillation. And when you look at this, you're actually seeing it with your eyes. You're not realizing that you're seeing it. But it's there, and it really pops out when you calculate the angular correlation function of those fluctuations. And this big booming peak here, called the Doppler peak, is the BAO in the CMB. It is on a co-moving length scale of about 150 megaparsecs. Now, you might say, well, look at all these bumps. Well, just higher harmonics of a single characteristic scale painted on the sky. So if you looked at, so this is the Fourier transform of the two-point correlation function on the sky. And so there is a unique length on the sky of 150 co-moving megaparsecs. That is the BAO. And when you Fourier transform it, you get all these Fourier wiggles, but it's a single scale. That's the important point. Where does it come from? It is a standard ruler. It is the size and co-moving, no, in proper coordinates, it is c over root 3 times the age of the universe at recombination. C over root 3 is the speed of sound in a photon plasma. The universe is mostly photons. Before recombination, it's, the photon to baryon ratio is 10 to the 10. So it's basically a photon plasma with a little bit of matter thrown in, and the speed of sound in the plasma is c over root 3. So what happens? When a fluctuation enters what we call the horizon, when the universe is going from the radiation-dominated era to the matter-dominated era, when a fluctuation of size L enters the horizon, meaning C times T equals that scale, it starts acting causally like a physical system. And these fluctuations will then, because they're overdense, they're overpressured, they will push out. And so this is a point perturbation that has just entered the horizon, and it pushes out a sound wave through the photon plasma at speed c over root 3. If you have a whole bunch of fluctuations, it does this. But you can pull this. So then this wave goes out until the universe recombines. At that point, photons and the matter decouple, and you've lost the pressure support for that acoustic wave. So they go out, and then at recombination, boom, they're just frozen there. There's a nice Physics Today article on this that I recommend. This shows the time evolution of one of these point perturbations through redshift. I don't have time to go through this, but the perturbation is in the photon plasma, and then at recombination, it just freezes. So think of every peak in the density field sending out this sound wave. And they are all going out, and then at recombination, those sound waves, superposition of sound waves, are just locked in. And what happens is the dark matter actually feels that potential, the potential well of the baryons, and that's what's shown here. So it's not in the dark matter, it's in the baryons, and then that's why it's called BAO. And then the dark matter catches up with that perturbation, and you get a feature in the dark matter power spectrum. So this has been found in the large-scale structure. This is galaxy large-scale structure from Sloan, and this is the characteristic scale on the sky. And it was found in by Eisenstein and company in 2005. So this is the galaxy two-point correlation function. And there you see, voila, this little bump at 100 H inverse megaparsec, which is 150, roughly 150 megaparsec. There's the signal. So it's there, and the point is, this signal should be in every form of structure in the universe, including the Lyman alpha forest. So that brings me to the present and the future. You've heard of BOSS, the Baryon Acoustic Oscillation Survey. So BOSS is just getting started, and it is going to collect redshifts of 1.5 million luminous red galaxies out to this redshift, but it's also going to collect 160,000 spectra of 160,000 quasars. Higher resolution spectra over this redshift. And so we want to be prepared to take advantage of that data.
We are going much farther than Redshift 3.
Oh, are you?
Yes, we are.
Oh, how high are you going?
For immanent forest, up to 4 is okay.
Terrific. The forest gets easier to see at higher redshift. So your statistic, so that's great news. Glad to hear that. So the BAO in the Lyman alpha forest has not yet been detected, at least as far as I know. Maybe you'll tell me otherwise. Huh?
It is.
It is? Okay. Is it published?
No.
No, very, very short.
Okay, good.
I'm looking at email right now.
Good. Glad to hear that.
About half the data.
Great. Great. I'm looking forward to that. Okay. So Lyman alpha absorption, which arises near mean density of the IGM, should show the BAO modulation with minimal redshift space distortion. And so two things. One is the BAO is a beautiful standard ruler. I mean, it is just a number. C over root 3 times the time at recombination. There it is, boom. Doesn't have systematics associated with the thing itself. And then your way of detecting it, the Lyman alpha forest, should be pretty clean because you don't have velocity space distortions at these low overdensities. You just need a large statistical sample in order to find it. So, simulating the BAO. The technical difficulty is the range of scales. So I told you that the wavelength is 150 megaparsec co-moving, and I estimate you need a box at least 4 times this size to contain enough modes. And the absorption filaments are about 100 kiloparsec thick. That is the Jeans length. And so you work this out, you'd like a simulation of size 6,000 cubed, which is big, even by my standards. So we started a simulation campaign, working our way up, 1,000 cubed, 2,000 cubed, 4,000 cubed. Different box sizes, different, different initial conditions as WMAP kept releasing new parameters. And that's where this simulation came from. This is our largest attempt yet. And I can tell you that we have not analyzed this simulation. We're still working on the warm-up simulation, which is 2,000 cubed. So the way you analyze this is you imagine there's quasars behind the box, and you take spectra. So each one of these has a line of sight spectrum. And then you calculate the cross-correlation function of the 2 absorption spectra. So that's analogous to the 2-point correlation function for galaxies on the sky. So we've done this with 5,000 random lines of sight. That generates over 12 million pairs. And what you can do is calculate the autocorrelation function. That's just along a given line of sight, correlate the spectrum with itself. You should be able to see the signal there, but in fact, we do not find the. So here is 150 megaparsecs. We don't find the signal to within statistical significance. So these are the 1 sigma error bars. So that's kind of interesting. But if you do the flux cross-correlation function, the signal comes out, and it's statistically significant. But you also see that there's some bumps that are not supposed to be there. We don't know what those are due to at this point. It could be just cosmic variance. Even though these are pretty big volumes, they're not gigaparsec volumes. And so maybe we're just seeing some noise, if you will, cosmic noise. But at least we're seeing the signal. This is calculating the cross-correlation function, separating according to column density of the absorption lines. So these are column densities less than 10 to the 16 per square centimeter, and this is above 10 to the 16. And you notice that the signal is actually larger in the high column lines, and I think that's because the high column absorbers are associated with galaxies. And so to a certain extent, we're doing the galaxy 2-point correlation function in H1 absorption. This shows the cross-correlation function of matter properties along these lines of sight, dark matter and gas, and you see the signal there as well. But you also see some of these satellite bumps, which may go away with further analysis. So I need to conclude now. Findings and implications. So detecting the BAO in the Lyman alpha forest is feasible, and I'm glad to hear that the observers agree. Based on synthetic observations, fully hydro simulations, we find that the signal is statistically significant in the cross-correlation function, but not in the autocorrelation. I'd be very interested to know whether you guys have seen the BAO in the auto. I don't know how long I have to wait to get an answer, but that's the first thing that I would want to know. The higher column density systems show the signal better, but they're rarer and have higher statistical error. And the signal is more sensitive to spectroscopic resolution than numerical resolution of the simulation. This is what we've seen comparing to the 1,000-cube simulation. So this is my last slide. We need to understand why the autocorrelation signal is so weak, and maybe it's not in nature. Redshift space distortion, masking by high column systems, not sure. Need to investigate the reality of the satellite peaks in the cross correlation, and much more work is needed to quantify the effects of resolution, redshift evolution, and other astrophysical effects. So now that I hear that BOSS is just about to release its first science result, I would say that right here, right now, you're at the beginning of a new era of scientific exploration, and that's an exciting place to be. Thank you very much.